Okay, so last time we derived the following statement. If we take Minkowski space and we take half of it, of course all the pictures I'm drawing are two-dimensional, but in higher dimensions it's half in the sense of just sending this straight into the board. If we take half of it and call this half region A, then in the Minkowski vacuum, which just means the usual vacuum, the one we usually talk about. In the Minkowski vacuum, the reduced density matrix in region A is thermal at inverse temperature 2 pi, but with the role of the Hamiltonian played by the boost charge, Ka. Yeah?
So we've never actually specified the acceleration of the observer, have we?
Getting there, yes. At this point, there is no observer. There is no observer. We're just talking about a quantum state. Okay? There's a quantum state, the vacuum, and that quantum state in region A is mixed. So we describe it by a density matrix, and this is its density matrix. And that's specifying what state it is. And now we could do physics using this result. And so that brings us to the physical consequences. But first of all, maybe I should emphasize that by design, all of the physical consequences here are independent of the fact that that we restrict it to Rindler space. Okay, so like if I calculate a 2-point function of operators like this, by tracing against the Rindler density matrix, then the whole point of the reduced density matrix is it's going to give exactly the same answer as calculating that 2-point correlation function in vacuum. Yeah?
How are we supposed to think of the half of space that we've traced out? Is it like the part that's behind the accelerating observer or something? Or?
I'm coming to the accelerator. I haven't gotten to no accelerating observer yet, but they're coming. So postpone that until we have an observer. Okay. So physical consequences. Well, the simplest and most striking one maybe is the Unruh effect, which says that uniformly accelerating observers detect a temperature T ops for observer is A over 2 pi, where A is the acceleration. Notice units here, so that the boost charge is dimensionless, so its corresponding temperature is dimensionless. The acceleration makes up for the units and gives a dimensionful detected temperature, so this is something we could like write down in Kelvin. Okay, once we have this result for the modular for the reduced density matrix, it's very easy to check this. So now I'm gonna show this. Just a comment on terminology. This thing that we derived, I called it Unruh. This is also called the Bisignano-Wickman theorem. Evidently, there was a totally independent people were deriving this at exactly the same time. I'm not sure which one came first, but this was like early 70s.
Can you spell that?
I'm sure someone can.
Tom?
Yeah.
Is there an H bar in the formula?
I'll put an H bar in a minute. Sorry, in that formula?
The temperature. I'm just curious if it's actually a quantum effect.
Yes, there's an H bar. Yes. Yeah. I'll put in the H bars and C's momentarily. Okay. Okay, so what does all this have to do with accelerating observers? Well, the world line of an accelerating observer, let me remind you of the Rindler coordinate system was minus r squared d eta squared plus dr squared plus dx perp squared. Eta is the Rindler time, which follows the boost trajectories. Okay, so a uniformly accelerating observer has world line of constant r, and we can choose that constant r to be r equals a inverse. The eta for that world line is then a times tau, where tau is the proper time. Okay, so let's just make sure that that's reasonable. Well, if we sit at constant r, set it to a inverse, that gives these hyperbolas, and that reasonably looks like the world line of a uniformly accelerating observer. To actually check this, you have to do a quick little calculation that I'm not going to do, but you can find it in Carroll. If we choose a larger acceleration, then a inverse is smaller, so larger acceleration is a more extreme accelerating path. So that makes sense. Now, the observer defines energy. What do I mean by defines energy? I'm not making a mathematical statement here. I'm making a physics statement here, like if they have a thermometer or if they have a camera that detects frequencies or whatever experiment they're doing, they define energy conjugate to proper time, to their own proper time, okay? Because we can always go to a local Lorentz frame near that observer. Proper time will just be the ordinary time in that local Lorentz frame, so that's the time they're going to use. So the vector, the vector in the unit, the vector in the time direction, in the proper time direction, is A inverse d eta, which means that energy, according to this observer, is A times the boost charge, because we said that the boost charge is conjugate to the eta direction. And then we have e to the minus 2 pi ka is e to the minus 2 pi over a e obs. And so according to this observer, the density matrix is thermal with respect to the actual energy that that observer uses with inverse temperature 2 pi over A. So that gives our, oh, I lost the formula. Oh, the formula's over there. T obs is A over 2 pi. That's it. That's it. We're done. So this is really the temperature that's seen according to the observer who follows one of these fixed R trajectories in Rindler space. Let's see. It's a real physical thing. If they have a temperature, if they have a thermometer, it will read this temperature. if we put in units, then T obs is h bar A over 2 pi C KB. To orient your brains here, if you want to get a temperature of 1 Kelvin, then you should accelerate at 10 to the 20 meters per second squared. It's not very hot. Okay. There's an h bar on top. This is quantum effect. There's a c on bottom. It's a relativistic effect. So we're not talking very hot. It's not going to burn you up. Questions? Elliot?
So,
should we go to Ryan?
no, so we traced out half of the space, which is like the left half of that diagram that you drew.
Yes.
And I guess the accelerating observer never goes through that part of space.
Yeah, the accelerating observer, the uniformly accelerating observer will remain in the Rindler patch. It causes development of region A. Yeah.
And so that's why I was trying to trace out the other half, because the accelerating observer is just computing local observables on that part of space.
That's right. That's right. I don't know if I said this last time. This line here is called the Rindler horizon. Okay, the Rindler horizon, of course, there's nothing special about it. It's just an imaginary place in Minkowski space. Everywhere is a Rindler horizon. I am sitting on a Rindler horizon at this very moment. So there's nothing special about it, but it has, as we'll see, it has many features that are similar to a black hole horizon. The reason basically being that locally, all space-time is flat. And so locally, a black hole horizon, you can think of as a Rindler horizon. And that's gonna basically give us Hawking radiation when we get there pretty soon. Okay, Ryan?
Is there any context where this sort of effect could be measured in the future, or maybe we can measure remnants of this sort of effect from like?
Can we measure the Unruh effect?
Yeah.
Not that I'm aware of.
I mean, obviously we wouldn't be able to measure directly. Inflationary effects.
There are analogous things that can be measured, like, yeah, I don't think so. I don't think so. This actual effect, like literally the Unruh effect, I don't think it's possible. Yeah, it's very closely related to Hawking radiation, and that's also very hard to measure unless we get lucky. I'll talk about that when we get there. Other questions?
Oh, except.
Okay, so this derivation that we gave of this physical effect of the reduced density matrix of region A, this is a complete derivation. I used path integral language. I purposely did not use the language of perturbative quantum field theory, and the result is non-perturbative. Okay, so even in QCD, where everything is strongly coupled, it's very hard to calculate anything, this statement about the reduced density matrix is still true. Of course, we can also use the language of perturbative QFT, and the reading for this week is a chapter in Carroll that does that. I'm just going to very briefly sketch how that is going to go. I'm not going to give any details at all. It's in the reading. It's for you to work through. But I just want to say the words. And also I can answer questions about it, about how to think about it. Okay, so if we think about free fields, And I'll talk about free fields in 2 dimensions, just to keep things simple. It doesn't really matter, just to sketch how this works. Okay, so free fields obey the wave equation, box phi equals 0. And this, of course, has the ordinary plane wave solutions that we're used to in Minkowski space. Okay, so in Minkowski coordinates, minus dt squared plus dy squared, the solutions are e to the minus I omega t plus I k y. And if I call this solution phi k m for Minkowski, then the quantum field phi, which I'll put a hat on, just to emphasize that this is the field operator, is the sum over k of ak phi k plus ak dagger phi k dagger, phi k star. And when we do quantum field theory, when we do perturbative quantum field theory in Minkowski space, this is the starting point. We quantize this field, and we define a vacuum, 0, to be the state annihilated by the annihilation operators, and we define excited states by acting with the creation operators. Okay, good. Now, we can also do quantum field theory in rindler coordinates, minus r squared d eta squared plus dr squared. So if we solve the wave equation in rindler coordinates, it again has plane wave solutions, like in Minkowski. It's a little different because the metric is a little different, so the wave operator will look a little different in these coordinates. But I'll write the solution for you. It's phi k is e to the minus I omega eta plus ik log r, where omega is the absolute value of k. That was also true for the Minkowski modes, but I forgot to write it. And we can define a field operator phi hat, which is the sum over k of bk phi k plus bk dagger phi k star. Okay, so we can do quantum field theory in rindler coordinates, just as we do quantum field theory in Minkowski. If we want, we can just follow the usual procedure, which is to define a vacuum state called that I'll call the rindler vacuum. So the rindler vacuum is the state that's annihilated by the BK.
Sorry, where is this mode expansion valid? Only in the rindler wedge?
That's right.
Okay.
Yeah. And just as in Minkowski, we can look at excited states, call them rindler particles, which you get by acting with BK dagger on the rindler vacuum, and you can act with more of these to create multi-particle states.
That's an A array, not A inverse.
Sorry?
That's an A, not an A inverse. Otherwise you would get the energy revision.
No, this is A inverse. I think. Did I get it wrong?
Well, so partial eta by partial tau is also A, right? So partial tau, I guess it's.
Would have to be A for the units to work out as well.
I mean, just converting partials, right? Partial eta by partial tau, partial eta is.
Well, it definitely has to be A inverse. I mean, if you the one that's more bendy is the one that's accelerating faster. Okay, right? So it definitely has to be A inverse. But you're right. Maybe I messed up an A inverse somewhere else. I think it was here. I think d tau.
Yeah, but you.
This one here should be an A, right?
Yeah.
Yeah. Okay.
Yeah, that probably sounds.
Yeah. Thanks. Now, we defined a Minkowski vacuum by the usual way. We defined a rindler vacuum by doing something similar in rindler coordinates. And the point is that the Minkowski vacuum, I'll put an M here, a Minkowski, just to be clear in this discussion, but that just means the one we always talk about, the actual vacuum state. The Minkowski vacuum is not the same as the rindler vacuum. That's clear from the way we define it. There's a different mode expansion, so there's a different definition of B. We could go through the coordinate change and relate A to B. You can find some relationship between A and B. It's called a Bogle-Yuboff transformation. And it'll be some non-trivial transformation. You'll read about it in Carroll. But if the mode expansions are different, then the vacuum states are different, and the definition of particle is different. So these are just not the same. And that is another way. So that, in the language of, that's how you understand the Unruh effect in the language of perturbative quantum field theory. What you need to do to find the finite temperature is ask the question, well, what is, if the vacuum states don't agree, what is the Minkowski vacuum in terms of the rindler vacuum? Or, well, it's not the vacuum, so it must be some excitations of the rindler vacuum. And what excitations does it correspond to? Well, it's the thermal mixed state. Okay, so that's kind of how it works. The way to think about it is that when you're doing quantum field theory in curved space, there isn't really a unique notion of vacuum, because you have, when you define the modes of the quantum field, you have to choose a time with respect to which physical modes are positive frequency. So there's a choice of time involved when you write down the mode expansion of the field. And this choice of time affects the definition of energy, and therefore vacuum and particle. And if you go through the details of the mode expansion, you'll end up with our same formula that we derived from the path integral. The boost charge here is exactly the frequency omega in the Rindler mode expansion, right? Because in the Rindler mode expansion, it's e to the minus I omega eta. So this frequency of the Rindler modes is conjugate to eta. And therefore, that frequency omega in Rindler modes is measuring boost charge, not ordinary energy. Okay. A couple of comments. So the first comment or question, let's say, is what does the state 0R look like? If the Minkowski vacuum is not the Rindler vacuum, then what the heck is this Rindler vacuum? The answer to that is that the Rindler vacuum is a vacuum in which an accelerating observer sees nothing. Okay, so this observer thinks that space-time is empty, doesn't see anything. But that state is singular on the Rindler horizon. It has T mu nu is infinite. I'm not going to go through the derivation of this, I'm just stating the result. So it's a very weird state. And it doesn't even make sense to talk about this state unless you're stuck in the Rindler patch. You know, if you're a Minkowski observer who travels on a world line like this, then you shouldn't think about this state. You shouldn't talk about this state. If you hit the Rindler horizon, you'll encounter a wall of fire, a firewall. Okay, so the word firewall, there's something in black holes called the firewall paradox, which we'll discuss later, but it's related to this fact. It's related to the fact that if you try to define a Rindler vacuum and then jump through the horizon of that Rindler patch, you'll encounter infinite energy as you try to do so. So this state is just no good.
Question?
Yeah.
In this case, we aren't assuming uniform acceleration, right? Because then it will be at fixed R.
Well, this statement about what the state looks like doesn't refer to any observer. The state has infinite stress energy on these horizons, and if you stay away from them, you might be okay, but if you hit them, you're in trouble. Right, you'll never hit them if you're a uniformly accelerating observer who's, well, of course, this uniformly accelerating observer will hit them. But as long as you're a uniformly accelerating observer in this Rindler patch, then you're okay.
When you say the state, do you refer to the state only defined in the wedge? Because you use B to define. B is only.
Ah, good,
Yeah.
good. Yeah, it didn't even. This discussion didn't really make a lot of sense because 0R is I defined as being a state in region A. So what I meant was we can put we can take the full space and put both Rindler wedges into the vacuum, and I was talking about the stress energy in this state, which is a very crazy state in Minkowski space. Jumping ahead a little bit, this is a state that's separable, right? So this is a product, separable or non-entangled state, and that's what made it so weird. Yeah.
Why do you need the double copy? Why can't you just define the Rindler state and then try and calculate some two-point function and show that it diverges on the horizon? Isn't that
You mean like just look at it close to the horizon?
Yeah.
Yeah, you could do that.
Two-point function.
I just don't know what it looks like there. I'm not sure whether it smoothly I don't remember if it smoothly diverges or if there's some delta function at the horizon or what it looks like exactly.
There should be a delta function because you can have accelerated observer in this rindler frame that gets arbitrarily close to that horizon.
Yeah, but they're going to be moving really fast. Yeah, I'm not sure. I'm not sure. Yeah. Yeah.
Sorry, I have a question.
Yeah.
So this singular energy momentum tensor happens in the Minkowski basis or in the, so because that state is the vacuum, so it can't have energy. It's the vacuum.
No, the Rindler state does have energy. I mean, it has energy. It has. I think it's going to be delta functions probably. I don't remember though. I think there's an infinite amount of energy localized here.
But so I guess my question is, this description of the fireball is a description of the Rindler vacuum in the Rindler basis, or the Rindler vacuum written in Minkowski basis?
It's a basis independent statement. This basis independent statement is that if you work in this state and you try to jump through the Rindler horizon, you will burn up.
Awesome.
So it's independent of the basis. Yeah.
So I guess if you work through this perturbative calculation, you'll be able to show that the spectrum is thermal, right?
The
The spectrum in the Rindler vacuum is thermal.
No, the
Sorry,
spectrum,
the spectrum
in
in
the
the
Minkowski
Minkowski
vacuum
vacuum is thermal.
is thermal and Rindler. That's right.
Yeah, but isn't this a stronger statement than that? Because you also this is a statement about that
It
state.
is. Yeah, it is. Yeah. So what Jivan is saying is that you can calculate this thing in the Minkowski vacuum, and you'll find that it's thermal. But this is a stronger statement. It also tells you about the higher moments of this.
So
And if
to
your
prove
interacting theory is it's a much more complicated statement.
So to prove that, we have to consider a lot of these operators, creation and arrest operators.
You mean to prove that it's
Yes.
this?
Yeah.
Well, in a free theory, I think it's actually sufficient to get the number density, and then I'd have to think about it, but I suspect that is enough to prove that you're in a thermal state in a free theory. But yes, in general, you'd have to prove it for multi-particle states as well.
Yeah, you have to show all correlations are also thermal.
Yes, that's right. So yeah, this is a in general much more powerful statement. This is some little version of this that you can show in a free theory. Okay, another comment. Question. What does Unruh radiation look like? Sorry, yeah. Unruh radiation look like to an inertial observer. In other words, if we have one observer who is accelerating and holding a thermometer, say the thermometer started at 0 temperature, then that thermometer is going to get excited because they're detecting a thermal state. So that thermometer is going to absorb quanta and go into an excited state, right? Now, if we also have a Minkowski observer, an inertial observer moving on this world line. So what does this person think happened? You know, this person thought that space-time was empty, and then just saw this thermometer do something weird. So what's up with that? Any ideas?
Work was put into to move the thermometer.
That's right. So it takes energy to uniformly accelerate. So what the inertial observer sees is, well, let me, write a formula. So the absorption would correspond to acting with a Rindler annihilation operator on the Minkowski vacuum. Right, because the thermometer is absorbing one of these rindler modes. But a rindler annihilation operator is not a Minkowski annihilation operator. It involves some mix of creation operators too. Okay, so BK acting on the Minkowski vacuum actually creates excitations of ordinary particles in the Minkowski vacuum. So what the inertial observer will see is that the thermometer will go into an excited state and emit some radiation at the same time. Where's the energy coming from? It's coming from the rocket booster that this person is using in order to maintain a uniform acceleration. Okay, questions?
Yes, I have one. So from the Minkowski perspective, is there a temperature associated with the accelerating, or whatever is accelerating, because it's emitting radiation?
Well, it depends what you mean. I mean, the fields are not in the quantum fields are not in a thermal state, according to the Minkowski observer. But of course, everybody, including the Minkowski observer, will agree that the thermometer went up to 1 degree. So in that sense, they agree on the physics, but they won't really call it a temperature because they won't see e to the minus beta energy distribution of quanta.
I have a question.
Yeah.
Maybe we will talk about this later, but in which sense is this different or similar to the Schwarzschild case? Like if I'm hovering outside of the black hole, and I see radiation because the black hole is radiating. Is that radiation being sourced by my rocket? Like because I'm hovering, so I have to do a force to stay there. So someone free falling into the black hole will think that I'm emitting radiation because of my rocket?
Let's come back to that.
Okay.
Let's come back to that later. 'Cause, yeah, if you're dying to know, you can ask me after class, but yes. We'll come back to it. I just want to point out a quick trick to get the en route temperature, because we're going to use this for black holes. So given a metric, suppose you didn't know where it came from. And I had just told you that we're going to study the Rindler metric. There's a very quick trick to see that this is thermal and at what temperature. Okay? So there's a trick to find temperature. And that's just a Wick rotate, eta to minus I, eta Euclidean. So that now ds squared is dr squared plus r squared d eta Euclidean squared. That's step one. Step two is to require that the Euclidean manifold be smooth. Smoothness at r equals 0 in this Euclidean manifold requires the periodic identification eta equals eta plus 2 pi. we can see that two ways. One way is just to notice that this looks like polar coordinates. And if you don't have the 2 pi identification, you're going to have a conical excess or defect there. Maybe a better way to say it is that on smooth manifolds, small circles have circumference 2 pi r. That has to be true on any smooth manifold as you take r to 0. So that has to be true around the origin here. Now, if we go back to Lorentzian, this means that eta is identified mod 2 pi I. And remember that at finite temperature, observables effectively have their time have periodic and imaginary time with period beta. Where beta is the inverse temperature. So we could just read off directly from this geometric identification that the temperature of this space is 1 over 2 pi. So often the way people say it is that it's smoothness at the horizon that gives you the temperature. It's really smoothness at the way I've described it here, it's really smoothness at the horizon of the smoothness of the Euclidean manifold at the horizon. Gives you the temperature, gives you the fact that it's the thermal state, and you can use that smoothness as a trick to read off the temperature. Okay. And just a few last comments about this calculation. Then we'll move on. So first, minus log rho A, which in this case is 2 pi Ka, is called the modular Hamiltonian. Or the entanglement Hamiltonian. People use both language. Yeah.
It's a little confusing to put these things together, but if you have a firewall at the horizon, it will back react, and the manifold need not be smooth there anymore, but there will still be a temperature associated with that side, right?
Well, if there's it was when we tried to turn off the temperature that we found the firewall. So I think if you try to go in the Rindler vacuum, there's no temperature anymore. There is a firewall. There isn't really a notion of temperature. Okay, so I think this nomenclature is sort of clear. You know, if you think about the thermal state, it looks like e to the minus beta h, and the point is that the modular Hamiltonian you can define for any density matrix in any state for any region, but it's just by definition you write the density matrix as e to the minus h, and you call that the modular Hamiltonian. Okay. It, in general, has nothing to do with the actual Hamiltonian of the theory. It's only in very special cases that you can even write it down. Okay. So only in very special cases, that the modular Hamiltonian can be written as the integral over region A of some local density or function of x. Okay, that was something very special about the calculation that we just did. I'm going to just list a few of the cases where this is possible. There's, of course, rindler in vacuum. That's what we just showed. The modular Hamiltonian was the boost charge. There's a ball-shaped region in vacuum in a conformal field theory. I think I'll give you that one on the homework. The reason that's, or one way to think about that one is that the ball-shaped region is conformal to rindler. Okay, so you get something similar. Another case is a two-dimensional CFT where region A is an interval at finite temperature. Again, there's a conformal transformation. Reason for that, I'm not going to go through it now, but I just wanted to let you know that exists. And the last example is Wiggly rindler. This is a generalization of rindler space where you take a null plane. This is supposed to be a null plane. And first let me draw rindler space. Okay, so if we, see I now have to draw the extra dimensions that I've been suppressing all this time. Okay, so rindler space is the half space to the right of the null plane, where we just take the it's nice and straight. Okay. So Wiggly rindler, that's not like the official name for it or anything. I'm just calling it that. It sounds ridiculous. Okay. Is where you take a general cut of the null plane and declare your region to be everything to the right of that. Does that picture make sense? It's quite remarkable that you can write down the modular Hamiltonian for this case. I'm going to write the formula just for fun. Okay, so if this is the t plus direction, the null direction, then this thing out of the board is x perp. Then a Wiggly rindler is defined by a function f of x perp, which is just the function that defines this And the modular Hamiltonian in this case is the integral over x perp, then the integral over the null plane, integral dt plus, from x perp to infinity of t plus minus f of x perp, stress tensor t in the t plus direction. There's some intuition attached to this formula, which is very interesting, which is that you would get the same thing if you just pretended that this was a bunch of two-dimensional Rindler spaces, one at each point along the transverse direction. So that's what this formula is saying. It's saying that you just, it's saying that all that everything factorizes in the transverse direction. So you just add up the contribution of all these Rindler slices along the transverse direction, and that magically gives you the right answer. This is telling you something non-trivial about the vacuum state of a QFT, that it can be factorized in this way. This formula was derived only a couple of years ago. It's a pretty recent result. Okay, so what does modular Hamiltonian look like more generally? Well, it's just terrible. Okay, so it's not local. It's not the integral of something local. It can just be some crazy non-local thing. And often you just can't write it down. There are some cases where it's non-local, but you can write it down. But they're few and far between. There's just a couple of very simple examples where you can do that.
Well, I mean, you could take any non-local permission operator and exponentiate it and get some state.
Yeah, good. I guess what I meant was, yeah, you can always define states that way. I guess what I meant was that if we started in vacuum, if we started in vacuum or in some reasonable state like finite temperature or with some operator insertions, then pick a region. Pick a region A that looks like this, or if you're in a 1+1 dimensional theory, pick a region A that has two disjoint pieces, then you just get something crazy and non-local. Yeah.
So to determine whether the Hamiltonian is local or non-local, do I have to calculate the state, or can I understand it from more general point?
Well, there's a sufficient condition. Okay, so and the so you write down the Euclidean path integral for rho A. In general, there could be lots of cuts. If there's a symmetry, and then we're going to slice this path integral. If there's a symmetry that takes you from one side of the cuts to the other, then that's sufficient to get a local modular Hamiltonian. But it's not necessary. A few years ago, I might have guessed that this was necessary and sufficient, but this is a counterexample. Okay, so this is a case where there is no way of arguing from symmetry that this is the modular Hamiltonian. So you can get lucky. Okay, last questions about this?
Sorry, regarding the previous drawing, when you said there is a symmetry that takes you from above the cut to below the cut, what exactly do you mean?
I mean, if there's a conserved charge that generates that flow. Okay. The next thing we're going to do is talk about the Thermofield double. I'm going to define this generally and explain how it's related to everything else that we've been discussing. Okay, so I'm not going to spend too much time on this now. I just have a couple pages on it. We're going to come back to it later, and it's going to keep coming back with black holes. But let's start from the beginning. Okay, so a state in a Hilbert space H1 times H2 is entangled if it's impossible to write it as a tensor product of a state in Hilbert space 1 with a state in Hilbert space 2. A density matrix rho is entangled if rho cannot be written as a sum of some weights wi, rho 1 I tensor product rho 2 I. We'll have a lot more to say about entanglement, but that's it for now. So purification is the statement that any rho can be purified. So let's say rho is associated to a Hilbert space H. Then that state can be purified by enlarging the Hilbert space. That is, by viewing this by adding an auxiliary Hilbert space and embedding the physical Hilbert space inside of it. So what does it mean to, yes?
Are these infinite dimensional spaces?
Not yet.
Okay, so I'm just trying to understand the difference between those two. So, and you can always, if something's finite dimensional, you can always write it as a sum of tensor products, right?
That's right.
Okay. So in the second case, so it seems like in the first case you're saying that it can't, you don't have a pure tensor basically. It's entangled, it's not a pure tensor. So it's not a sum.
Well, if it's not separable, so states that look like this are called separable.
Yeah.
So if it's not separable, it's called entangled.
Okay, but it is a sum of basis elements of H1 and H2.
Every state is, yes. Yeah.
Okay,
Let me write, okay.
But then for the
Simple
case of
example.
rho, so I guess my question is really about the case of rho. The fact that it can't be, it's like you're saying it can't be written as some kind of basis. I'm wondering why.
So an example is this state. So this is an entangled pure state.
Yeah.
It's a sum of separable states. Everything's a sum of separable states, but it cannot be separated. And if we make the density matrix for this, it looks like this times 0, 0 plus 1, 1. And that cannot be written in this way. So it's just the same statement, but for density matrices. This one's more general because it allows it to be mixed. Okay, so any rho can be purified by enlarging the Hilbert space, i.e. there exists a state psi, a pure state psi, in H times H ox. We can define the density matrix rho psi associated as pure state, which is just psi psi. And rho, our original state that we're purifying, is the trace over the auxiliary space of rho psi. We started out with a state that could be mixed, rho, and we've said that we can realize this mixed state as a pure state, but in a bigger Hilbert space. That's what purification does. And in particular, any observables that we want to calculate, like trace O1, O2, dot, 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 rho, are then going to be equal to expectation values in the state psi. And you can therefore turn any mixed state calculation into a pure state calculation. Additionally, we can always choose the auxiliary space to have dimension less than or equal to the actual original space. Or if we want, we can just choose it to be another copy of the physical space. Proof. Diagonalize the density matrix. Rho is the sum over I of pi I. Then we can choose our purification psi to be the sum over I of the square root of pi times 2 copies of the state I. So in the diagonal basis, we can purify just by taking each of the pieces of our density matrix and entangling it with a copy of itself. That's what this is saying. I'll leave the rest of the proof as an exercise, but you can check that the trace over the auxiliary space of psi psi is equal to rho that we started with. Couple comments. Purification is not unique. Of course, we could always just tensor in some extra junk. And when we do the partial trace, the extra junk will just go away. And secondly, the reason this is working and the way to think about it is that one way to make a mixed state is to take a pure state and trace out part of it. And what purification is saying is that any mixed state can be made that way. And it's the entanglement of psi, the entanglement between H and H auxiliary, that leads to the fact that rho is a mixed state. So the Thermofield double is this idea applied to the thermal state. Okay, so the thermal state is a mixed state. We can create any mixed state by doubling the system and tracing something out. So if we think of this thermal state on the Hilbert space H, then to make the Thermofield double, we double H to H copy 1 times H copy 2. These Hilbert spaces are identical. I just put the subscripts on there to keep track of them. Then the definition of the Thermofield double state is 1 over the square root of z of beta. That is the sum of energy eigenstates n of e to the minus beta en over 2, n copy 1, n copy 2. I've just taken the formula that we had up a minute ago and applied it to this density matrix. Okay, this e to the minus beta en over 2. This is the square root of pi that we had in the previous formula. Question?
Yeah. So we saw that if we start in the Minkowski vacuum and trace out half of space, then we get this thermal state. And of course, that doesn't imply that the Minkowski vacuum was a Thermofield double state to begin with, but I'm wondering whether it is maybe a thermal state written in the rindler.
It is. It is, and I'll come to that. Yeah. Okay. It's conventional to put a tilde on one of these. So let me explain why. In QFT at least, I don't know if people do this in other situations, but the reason for this, so the tilde is the CRT conjugate state. Okay, so what is CRT? It's like CPT, but instead of parity here is reflection. Okay, so this is charge. R means y to minus y, and t is the usual time to minus time. So it's like CPT, but the point is it doesn't act on the transverse directions. It only acts on the two directions that I've been drawing on the board. Okay, the CRT, so we take the CRT conjugate. Well, the reason for this is, I'll come to the reason when we have applications, but it's really, it really is just part of the notation. Just think of it as part of the notation, because if we wanted to, we could just declare anything with a 2, with a given state, but with a 2 here refers to the CRT conjugate state compared to this state with a 1 here. Okay, so let's not worry about this for now. I'll come back to it and explain it if we need it later. Okay, so this is a purification of the thermal state, and by definition, what that means is that for O's acting on the original Hilbert space H.
So can I ask a question?
Yeah.
So, are you assuming that your theory is CRT invariant? Because the energy En is also the same as En tilde, is it?
Oh, that's a good question. Yeah, I suppose I am here. I think we could generalize it to theories that are not CRT invariant, but I think I have assumed that here. Yeah. So for O's acting only on H1, expectation values in the Thermofield double state are equal to 1 over z trace e to the minus beta h of 102 dot dot dot. So the observables in this pure state are thermal observables. They're equal to the observables in the thermal state, and that was by construction. If you want to check this, I recommend going home and taking the partial trace of this, tracing out the auxiliary space, and make sure that you get the thermal density matrix. Note that there's an isomorphism that relates operators density matrices on one copy of the Hilbert space. To states psi on 2 copies of the Hilbert space. Okay, this is just because operators have, so an operator like rho has 2 legs, and so we can either think of, if we have something with 2 open legs, we can either think of one of those legs as being on the right, and one of those legs as being on the left. Let's think of this as a density matrix. Or we can think of it as a state in a doubled Hilbert space. The isomorphism, if you want it explicitly, is just that you take a basis for the, so this is a basis of states in the doubled Hilbert space, and you identify that with this operator on the single Hilbert space. And under this map, the Thermofield double state, which remember is on the double Hilbert space, h times h, is the same as the square root of the thermal density matrix, which is e to the minus beta h over 2. So on the right-hand side, we view this as an operator. On the left-hand side, we view it as state, but you can go back and forth between these two descriptions. And if you go back and look at our Thermofield double state, you can see where I got that e to the minus beta h over 2. If I had put one of these ends backwards, then we would have called this the operator e to the minus beta h over 2. Just by flipping it around, we reinterpret it as a state in the double Hilbert space.
So can rho be any operator, or it should be like a density matrix type operator?
Let's see. Yeah, we need it to be, I think we need it to be a density matrix. Yeah.
So where does positivity come in?
Let's see. We can always do this. Okay, now I'm confused. I have to think about that. Let me come back to that. Unless somebody knows the answer. Okay, I'll come back. I got to think about it afterward. Afterward is now. Sorry, go ahead.
So the tilde, wait, what was your question by the way? I'm sorry.
The question was exactly what the isomorphism is, whether it's just density matrices, which are special operators that are positive, trace one.
I think it's all matrices. I think you're just arranging the entries in a matrix into a column vector.
Yeah, that's, yeah.
So, you don't require positivity. But anyway.
Yeah, okay, that sounds right.
Yeah, but my question was, it seems like the tilde should come from, should come from how you're defining the auxiliary space.
Yeah.
Right?
Yeah, we could do a unitary on the auxiliary space without affecting the partial trace, the reduced density matrix. So there's a choice there of how we want to do that. In QFT, we usually do put the CRT conjugate there for reasons that we'll come to, but basically because when you do a path integral, the thing you naturally get is the thing with the tilde there.
Okay. Because sometimes I see that operators are mapped from one side of the space to the other via transpose, and I was wondering if that's how we get to.
One side of what space? This space?
Yeah, so if you double the space by just making a copy, then I think you should be able to map an operator on one side to the other by transposing that. So, as in like.
Oh, I see what you mean. Yeah.
Is that like what that is, kind of, or?
It's more than that because it's acting on momentum or on space-time, but I think it's similar. Okay, we're done. We're stopped. We're done.